Right, let's continue the foundation engineering class on the chapter 4. Maybe this one will be the last lesson on this chapter of special cases. It should be uplift capacity. It is not on the rock. We did this one, I think, last time. Okay, yeah, it is the uplift capacity of foundation. Okay, the last part of this chapter. So sometimes we need uplift foundation. Foundation can be subjected to uplift forces. Okay, it means the forces are acting, pulling out, trying to pull out the foundation. Okay, and sometimes we need this kind of thing when you have, for example, uh, the uplift, for example, on the bottom of excavation, sometimes to avoid the uplift due to water seepage. Okay, hydraulic failure. You sometimes need this kind of foundation to resist the force of water trying to lift the bottom of your excavation. But anyway, we need to know how to design foundation to stand the uplift forces. Okay, you can see the foundation like this, and the force acting on the foundation in this case is not downward, it's upward. Okay, the ultimate capacity QU we are looking for here is this one. Okay, so how will the failure happen in the soil? As you can see this time, the failure surface are like this, these lines. Okay, yeah. So it is not similar to when the load is downward, where we have general shear failure, uh, punching failure, or this kind of type of failure. We don't have this here. We will have this kind of failure. Okay, so we will use this failure mode to try to investigate the ultimate capacity. And this is, as I said before, ultimate bearing capacity is based on the failure mode. DF is the embedment of your foundation. Okay, so during the design process, it is very important to make sure that the factor of safety against uplift failure is achieved, a good factor of safety. Okay, so in this section we are going to talk about this equation, how to estimate the uplift capacity of foundation in both granular soil and cohesive soil, like in sand and in clay, both cases. Okay, so we start first the capacity in granular soil. It means the soil doesn't have cohesion is 0. Okay, so this figure is showing this is continuous footing, okay, being subjected to uplift force. Okay, so when it reach the ultimate load, when this load reach ultimate one, we can see this failure. I already explained the failure happen in the soil. So the ultimate load can be expressed in the form of this, in this way, non-dimensional. And this FQ is breakout factor FQ. Okay, so what is this FQ? Is equal to ultimate capacity divided by A gamma dF. The QU we know it already. This is, yeah, the definition. I mean, it is not, I don't mean the value. The definition of QU we know it already. Okay, A is simple, is the area of the foundation. Please, it is not the section, the width of the foundation. This means area. Okay, yeah, because as you can see, this section above the soil, the foundation is important, is supported by the area. Anyway, this A is not the width as we used to do in the previous part of this chapter. Not B. It is the area. So it is B multiplied by maybe L, the length of the foundation. Okay. So gamma, I think you know already, is the unit weight. It's written here. And DF also I explained it, the depth. depth of the foundation, okay? So what is important for us here is to find the breakout factor, because if we found it, since we know already A, we know gamma, we know DF, it will be easy to obtain the ultimate capacity QU, okay? So this breakout factor is function of what? It's function of the friction angle, this phi, and it's function of the relative depth, relative embedment, DF divided by B, okay? So please understand from here, we are going to look for this breaking out factor. We are not going to attack directly this QU, okay? We are going to search for this one, okay? And if we have this one, since these are known already, it will be easy to obtain this QU. It will just by just multiplying this, okay? So the breakout factor is a function of friction angle and df bar b. All right. So let's keep this here, this equation. So for a given soil friction with friction angle, this factor FQ, breakout factor, it will increase with the value, with the increasing value of df bar b. This is just means that the factor, the breakout factor FQ will increase with the depths. If the depths increase, it will increase, but at certain point, it will become constant, okay? The depths from which it becomes constant, we will call it critical depth, okay? CR means CR standing from critical, okay? So please remember that it will increase. The beginning increase, when the depths increase, it increases. The depths increase, it increases. At certain depths, when it reaches certain depths, it stopped increasing. So DFs becomes FQ becomes constant. Okay. So for, and this definition is very, very important because we will articulate this lesson around this. If the DF bar B is less than the critical one, then our foundation is called shallow foundation. Okay, please remember that. Okay, so in that case, the F for shallow foundation in circular or square, circular foundation and square foundation, because in case of circular foundation, we consider that the side is just similar to the side of a square foundation. So for these two, this is the equation we have for FQ. Okay, so this equation, remember, it is for shallow foundation, and shallow foundation means in this definition the df bar b is less than the critical one. That's his first point. Second point, this is for circular and square foundation. In this case, b, in case of circular foundation, b will be just like radius of the foundation. Okay, b here and b here. And in case of square foundation, b is like the side, the length of the side of foundation. And now for rectangular foundation, still for shallow foundation, but rectangular this time, you have this equation. Okay, you will say, what is m? What is ku? Don't worry. M is the coefficient which is the function of phi. We will see it also. Okay, because we need this FQ to get our bearing capacity, and for to get FQ breakout factor, we need M, of course, and we need KU. What is KU? Is nominal uplift coefficient. We will see all this. Okay, so we will start getting these. Okay, reverse. We will do in reverse way. Get these before going to get FQ, and if you get FQ, you get the ultimate bearing capacity. But don't worry, we will see step by step how it was, how we can obtain the ultimate bearing capacity. Okay, so for shallow foundation, it means df less than critical one. Okay, shallow foundation, circular, and square foundation, it is this. This is just the same equation I go to the previous slide, this one. Okay, it is this one. So